Dear friends, this is the continuous video related to the uh, design of the coupling. I was discussing in the last video, that was the design of the coupling. Now I will explain one questions related to the flange coupling. So this questions is that design a rigid flange coupling to connect two shafts. The input shaft transmit 37.5 kilowatt power at 180 rpm to the output shaft through the coupling. The service factor for the application is 1.5. Select suitable material for various parts of the coupling and specify the dimension of its components. The solutions of this problem is that first we have to select the material. Selection of material. The shafts are subjected to torsional shear stress on the basis of a strength plain carbon steel of 40 C8, whose ultimate tensile yield tensile strength, that is the sigma yt, is 380 Newton per meter square is used. The factor of safety is assumed to be 2.5. The key and bolt are subjected to shear and compressive stresses on the basis of the strength criteria. Plain carbon steel of grade 30 C8, sigma yt is equal to 400 Newton per mm square is considered for the key and the bolt. It is assumed that the compressive yield strength is 150% of the tensile yield strength. The FOS for the key and bolt is taken as 2.5. The flange have complex shape, and the easiest method to make the flange is is casting gray cast iron FG200, whose ultimate tensile strength sigma ut is equal to 200 Newton per mm square is selected. It is assumed that the ultimate shear stress is one half of the ultimate tensile strength. FOS is equal to 6 assumed, since the permissible stress is based on the ultimate strength as not on the yield strength. Permissible stress is, first we have to find the permissible stress. For shaft shear stress is equal to yield shear stress divided by FOS, which is the half of the ultimate tensile strength. That is the 0.5 sigma yt by FOS, 0.5 into 380 by 2.5. So it becomes 76 Newton per mm square. Key and bolt. For key and bolt, tau is equal to tau I by FOS, 0.5 sigma yt by FOS. So it becomes 80 Newton per mm square. Sigma c is sigma yc by FOS, 1.5 sigma yt by FOS. So it becomes 240 Newton per mm square. For plane shear stress is equal to ultimate shear stress by FOS, 0.5 into sigma u2 by FOS. It becomes 16.67 Newton per mm square. First we have to find the diameter of the shaft. Torque applied on the shaft, if you know the power transmitted, so power multiplied by this one service factor 1.5 divided by 2 pi n, so it becomes the 2984155.18 Newton mm. Shear stress from the torsion formula of 16 T by pi dq, so 76, that is the shear stress, shear 76 is equal to 16 into tau divided by pi dq, so d is equal to 58.48. so it can be assumed that the 60 mm. Now already I explained the how can select the numerical values of the diameter of the shaft. This is the 2 times diameter of diameter of the hub, 2 times the diameter of the shaft, so it becomes the 120 mm. Length of the flange 1.5 d, so it becomes 1.5 into 60, that is the 90 mm. D1, that is the pitch circle dia of bolt, that 3d is equal to 3 into 60 is equal to 180 mm. TF is equal to 0.5d is equal to 0.5 into 60, that is the 30 mm. T1 is equal to 0.25, D is equal to 0.25 into 60, that is the 15 mm. T1 is the thickness of protected portion of the flange. D2 is equal to 4D plus 2T1. If T1 is given, so you have to take the 4D plus 2T1. So it becomes the 270 mm. Design of the hub. Torque applied on the hub is equal to pi by 16 shear stress d4 minus a small d4 by d, where capital D is the diameter of the hub, that is the outside dia of the hub, and it is the 120. So from this formula you have to find the shear stress. Shear stress becomes the 9.38 Newton per mm square. This shear stress is less than permissible shear stress 16.67 Newton per mm square. So design is safe. Now shear stress in the flange at the junction of the hub. We have to check the shear stress at the junction of the hub. Already derived torsional moment is equal to pi d tf shear stress into d by 2. So tau is equal to 2t divided by pi d square tf. So it becomes 4.40 Newton per mm square. So shear stress tau is equal to less than 16.67 Newton per mm square. So stress in the flange are within the limit. Diameter of the bolt, diameter of shaft is 60 mm, and already I explained that if the diameter varies, diameter of shaft varies from 40 to 100 mm, number of bolts should be considered 4. So T shear stress transmitted by bolt is equal to pi by 4 dB square. dB is the dia of the bolt, n is the number of bolts, shear stress into d1 by 2. So dB is equal to 8t divided by pi d1 n tau. So it becomes 8 multiplied by this one. So dB, that is the diameter of bolt, is equal to 11.49. So consider the 12 mm. The compressive stress in the bolt is determined by shear stress tau is equal to dB tf sigma c d1 by 2 into n. So sigma c is equal to 2t divided by dB tf n into d1. So it becomes a 23.03 Newton per mm square, which is less than 240. That is the permissible shear stress, 240 Newton per mm square. Dimensions of key. Now you have to find the dimensions of key from the table. Standard cross sections of flat key for the 60 mm diameter shaft is 18 into 11 mm. The length of key is equal to length of the hub, or L is equal to 90 mm. So dimension of flat key are 18 into 11 into 90 mm. Torque, T torque, already I have derived this formula. Torsional moment is equal to W L tau into D by 2. So shear stress 61.4 Newton per mm square, which is less than 80 Newton per mm square. So check for the crushing stresses. So tau is torsion moment is equal to L into T by 2 into D by 2 into sigma c. So sigma c is equal to 4t divided by LTD, and it becomes 200.95 Newton per mm square, which is less than 240 Newton per mm square. So shear and crushing stresses induced in the key are within the permissible limit. So this one is the one questions related to the flange coupling. You can also do the practice from the books. You have to select the questions and you have to solve yourself. So this flange portion, the coupling has been finished, and in next video I will upload the other chapters. So thank you for your watching and patience.